an analytic technique for looking at solutions to differential equations. In this lecture, we're going to look at a qualitative technique where you can just think about what does the solution curve look like without having to actually calculate anything, and a numerical technique called Eulers' method. So remember that the geometric interpretation of a derivative from Calc 1 is that the derivative, dy dt, that's the slope of a tangent line. That's the slope of a line tangent to the curve y of t. So the right-hand side of a differential equation, anything that's on the right-hand side, it's got some t's and some y's in it, it tells you slopes at various points. You can plug in a t and a y and find out a slope at various points on the graph. So we can get a rough idea of what the graphs of the solutions look like by sketching a slope field. You can sketch little slopes at a bunch of random points. So we select some random points in the ty plane. So I use t because so many of the models for differential equations involve time. So we tend to use t and y instead of x and y. And then I'm going to compute the slope dy dt at each of these points. And then at each point, we draw a tiny little line with that slope, and that represents a tangent line to the curve. Once we have a lot of little tangent lines, you can try to trace the shape of the curve by following the tangent lines. So we'll do a quick example here. I've got dy dt equals y minus t. It's not separable, right, because that y and t are separated by subtraction and not multiplication. So I have to look at the solution qualitatively. So I'm just going to pick some random points in the ty plane and calculate the slope of the tangent line by plugging that t and y into the differential equation. So y minus t, 0 minus 0 is 0. 0 minus 1 is negative 1. So let's pick a few more, like 1, 1. Y minus t is 0. How about 0, 1? 1 minus 0 is 1. Negative 1, 0. 0 minus negative 1 is 1. 0, negative 1. Negative 1 minus 0 is negative 1. Negative 1, 1. 1 minus negative 1 is 2. And negative 1, negative 1. Negative 1 minus negative 1 is 0. And 1, negative 1. So I'm just picking some integer points that I can draw mini tangent lines at. So it comes out to negative 2. So at 0, 0, my slope is 0. So I go to the point 0, 0, and I draw a flat little tangent line. Go to the point 1, 0, and my tangent line has a slope of negative 1. So you draw a little slope of negative 1 there. At 1, 1, this point in my graph, my slope is 0, so I draw a flat line. Negative 1, 0, my slope is 1. So I draw sort of a line y equals x, but really small. And let's see what else I'm at. 0, negative 1. That's here. My slope is negative 1. At negative 1, 1, negative 1, 1, my slope is 2. So it's kind of steeper than my other one here. And negative 1, negative 1, my slope is 0. Put a flat one here. And at 1, negative 1, my slope is negative 2. Did I miss 0, 1? Slope is 1. There we go. So sketching slope fields by hand is very tedious, and like my slope of 1 versus my slope of 2, it's like hard to distinguish. But a computer can do this really well, right? Because you can do lots more points. It doesn't have to do just integer points, and it can really differentiate with the slopes. So it's best done using a computer. Your graphing calculator can do it. whether you have an 83 or an 89. Your 83 might need a special program that I put a link of where you can download it. Your 89, it's built in. And then free graphing software like GeoGebra can do it too. What? Sorry. Oh, okay. So here's a more detailed slope field for that same differential equation that we just did a few by hand. I created this using some software, some computer software. I can't remember what I used. But you can start to see what the solution curve might look like for given initial conditions. You can pick a random initial condition, like if I pick right here as my initial condition. So that initial point looks like y of y of 1 equals a half, something like that. Right? So if I want to sketch the solution that corresponds to that initial condition, I just kind of follow the slope field. Those are mini tangent lines to the curve, something like that. This point is at 1 comma 1/1/2, right? Yeah, so that's my initial condition. Y of 1 is 1/2. So here's just a bunch of solution curves sketched in there for different initial conditions. All right, so some technology you can use to create slope fields. Here's a link. You can get a program for your graphing calculator. Here's directions on how to do it on an 89. In GeoGebra, in the entry field, you just type slope field, and then you put in the right-hand side of the differential equation. Okay, so we're going to move from qualitative slope fields, where you just kind of like picture the overall shape of the graph, to a more precise numerical method called Eulers method. So we're just going to think about slope for a minute. Okay. If the slope of that line is 2 and the change in x is 3, what's the change in y? 6, because slope is always change in y over change in x, right? Slope is change in y over change in x. So in this case, I put in, I know the slope, change in y over 3, multiply both sides by 3, and you get delta y has to be 6. Okay, so in general, since slope is change in y over change in x, then you can also always solve for delta y by multiplying both sides by delta x. So delta y is m, the slope, times the change in x. Okay. Pretty straightforward, simple concept. We're going to apply this to finding a numerical solution to differential equations. Okay, so Euler's method gives us a precise way to draw a particular solution by following the slope field. It's much more precise than just like, ooh, kind of like follow the lines. So it takes advantage of the fact that the tangent line approximates the solution curve when you're near the point of tangency. So here's an initial value problem. dy dt is t minus y squared. Again, this isn't separable. I can't solve it analytically, not yet anyway. And I'm given an initial condition y of 0 equals 1. So here's the slope field. If I want to follow the slope field to sketch the solution to the initial value problem, my initial value is y of 0 is 1. So 0, 1 is my initial value. And then I want to just kind of follow the slope field. So it's going to go something like that and that. Okay, so I want to use my sketch to estimate y of 0.5. So here's 0.5. I go up to my sketch. What does it look like the y value is there? Sure, 0.8. So I'm going to say y of 0.5. According to my sketch, it looks like 0.8. And let's try y of 2. Go over to 2, go up to my graph. That was a terrible horizontal line. 1.3 maybe. Okay, I want to get a better estimate for y of 0.5 rather than just drawing a sketch there. So I'm going to draw a picture to help me. So y of 0.5. So I know that I can use a tangent line to approximate the function near the point of tangency. Now, I know something about the function at 0. I know the exact correct value at 0. Right here, I know that value. That one point on my graph I know is correct. So I could draw a tangent line there. And as long as I'm near the point of tangency, that tangent line will approximate my function. Now, 0.5 is arguably not very close to 0, but we're going to use it for this first example. So if my purple line approximates the pink curve, and I would like to know the y value at 0.5 on the graph, I could find the y value at 0.5 on the line instead, because it approximates the curve. So I know that this is 0.5. Delta y is what I'd like to know, because that will tell me I can subtract from 1 my delta y and figure out where my y value landed. What I need to know to be able to figure out delta y is the slope of this line. Do I know the slope of that line, or can I figure it out? Yeah, the slope of the line tangent to the curve is the derivative, right? I have a formula for the derivative, right? So dy dt, I'm going to evaluate that at the point 0, 1. That's the point of tangency. So that's going to be 0 minus 1 squared, negative 1. So the slope of this line I know is negative 1, and then I can solve for delta y. So delta y is my slope times delta x. I used the formula for the slope. Plugged in the point of tangency. Okay, my slope is negative 1. My delta x is 0.5, so I get negative 0.5. That's my change in y. That's this distance here. So if I started at 1, so I know that y of 0 is 1, y of 0.5 would have to be what? I was at 1 and I changed by negative 0.5, so my new y is 0.5. Now this is all approximate because I'm using a tangent line approximation to figure out these values. Okay. So it's close-ish to my visual approximation of 0.8. So there's just a more numerical way of doing just what we did when we followed the slope field. Okay, which part? Yes. So then I said, so I drew a little line here. I said that means that the slope of this line is negative 1. I know that the change in x here is 0.5 because 0 to 0.5, right? And I'd like to know delta y. So you can always calculate delta y by multiplying your slope times delta x. So I put in negative 1 for my slope, 0.5 for delta x, and I got the change in y. So my old y was 1. This point right here had a y of 1. After a change in y, I know that my change in x was 0.5. My change in y was negative 0.5. So I started at 1, I went down by 0.5, so I landed at 0.5. So this is just yes. Yes. No, no, just gives us 1 point. Yeah. Gives us some information about 1 point on the graph. I started knowing the value of exactly 1 point. I just did some calculus / algebra, and I found out an approximate value for a second point on the curve. You have to do this over and over and over again to get a picture of the graph. So you continue to get estimates for y of 1, y of 1.5, and y of 2, and this table will help us organize our work, okay? So k is just what step we're on. So let's see, when I started, we'll call this step 0. I was at the point 0, 1. That was my initial condition. And I calculated the slope by plugging in my t and my y into the differential equation, and I got, let's write this down, this is t minus y squared. So I got -1 here. Delta t was 0.5 because I was asking you about the value of the graph at 0.5. Okay, so that was like a given piece of the problem. And we calculated delta y by multiplying our slope times delta t. And we got -0.5. And then we have a new point, right? Next step, my new point, my new t value is 0.5. And my new y value, you take your old y value and add the delta y. So my old y value was 1, add -0.5, and I get 0.5. So my new point is 0.5, 0.5. That's an approximate point on the curve. 0, 1 was exact because it was given. Now I'm using the tangent line approximation to find a new point on the curve, an approximate new point. And then I do the whole process again. I use 0.5, 0.5, and I calculate the slope at that point by plugging into the differential equation, t minus y squared. So this comes out to 0.25. 0.5 minus 0.5 squared. And my delta t is still going to be 0.5 because I'm looking for y of 1. Delta. No, because I'm at 0.5, right? My t value is 0.5, and I'm curious about a t value of 1. So I'm moving from 0.5 to 1, so my change in t is a half. And then my delta y is my slope times my delta t. So 0.25 times 0.5 is 0.125. It's my change in y. So then I go back. Now I'm at step 2. Okay, my new t is my old t plus my change in t. So 0.5 plus 0.5 is at 1. My new y is my old y plus my change in y. 0.5 plus 0.125 is 0.625. And now I have a new point on the curve, an approximate new point on the curve. Plug these values into the differential equation formula. So I have 1 minus 0.625 squared, and I get 0.609375. Delta t is staying at 0.5 because I asked you to find y of 1.5, right? So my old t was 1. I want to know y of 1.5, so my change in t is 0.5. Delta y is the slope times delta t. And that comes out to 0.304687.5. That's it. So my next step, my line 3 here. My new t is my old t plus my change in t, so I'm going to be at 1.5. My new y is my old y plus the change in y, so 0.625 plus 0.304, blah, 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 is 0.9296875. Plug in my t and my y into t minus y squared, formula for the differential equation, and you get 0.63568 dot dot dot. You don't want to do any rounding until the end because you're going to, rounding errors can propagate throughout the method. Delta t is still 0.5. Delta y is dy dt times delta t. And I get 0.3178 dot dot dot. Okay, now I'm almost done because the last thing I asked you to find was y of 2. So in my last step here, my new t is my old t plus delta t, so I get 2. My new y is the old y plus the delta y, and I get approximately 1.25. And I don't have to calculate anything else because that's what I asked you to find, y of 2, 1.25. When you, at the very end, you can round. So this is how you do Euler's method. It's all based on using a tangent line approximation to the curve. It's much better suited to a computer, right? Because of all this, like having to write out all these decimals and like you're doing the same thing over and over and over again. And this is your first project, to implement Euler's method using Excel. I have it with me. I'll hand it out in a minute. When's what? Right now. I don't think I did. No. It's pretty. It's. If you've never used Excel, like feel free to stop by my office and you'll pick it up really fast. You know algebra, then you can use Excel. Project 1 is not due till March 7th, so it's not like, you know, you have to turn it around in a week. You get time to figure it out.